So far we have talked about many distributions in this class. Suppose this is the set of all possible distributions. Some of these distributions were discrete, like Bernoulli or Poisson or geometric. Then we had some distributions that were continuous, that is, they had continuous CDF, and these were disjoint. Now among these continuous CDF things, we considered a special subset of all those continuous distributions that have density. Examples are uniform 0, 1, exponential, gamma, etc. Now we will notice all our discussion basically pivoted around only this set in SEM2 and this set in SEM1. What happens to the other things? Are there distributions here that are neither discrete nor continuous? Are there distributions here that are continuous but do not have densities? The answer is yes. In this video, we shall take a look at an example from here that is neither discrete nor continuous. When I say not discrete, I mean there is no countable set A such that x only takes value in A. Probability x lying in A is 1. And when I say it is not continuous, I mean that the CDF is not continuous. Suppose we are trying to measure some quantity using a meter like this. Now the quantity that we are trying to measure is x, and that is given to be a continuous quantity, a continuous random variable. What do I mean? By this I mean I take a random object and put it inside the machine and I measure this variable for that object. Because I have chosen a random object, maybe I am taking some random piece of stone and trying to measure its weight. So in that case, x is random because the object for which I am measuring it is chosen random. Now this meter, in this case, it is showing the value of x. But most real life meters have an upper bound beyond which this indicator will not go. So if the true value happens to be something more than this maximum, which I have denoted by m, in that case the indicator gets stuck at m. So if you find that the indicator is at m, then all that I can actually say is that x is either m or greater than m. Now the reading that I get from the dial, if I call that y, in that case y is basically equal to x if x is less than m, and m if x is greater than or equal to m. Now what will be the distribution of this random variable y? Suppose that this is the CDF of x. You see, it is a continuous thing. Now for y, it will go on just like this up to m. But the moment you come here, it just jumps up to m. So the CDF will now look like this. This is also a non-decreasing right continuous function. Now you see this CDF is not corresponding to any continuous distribution because there's a jump. It does not correspond to any discrete distribution because for a discrete distribution it will be a step function with countably many jumps. Here you are increasing. So y is neither discrete nor continuous. Colloquially, we sometimes say, wrongly, but we do say it, that y has density up to this point and mass at m because there is a jump. But strictly speaking, it is neither continuous nor discrete. We often have to work with such random variables. These are called truncated random variables. Y is obtained by truncating x from above at m. Similarly, you can truncate it below if there is a minimum beyond which the indicator will not go. This exercise has a very similar setup, except that now I have also a minimum. So now the truncation is like this. If x falls below m, it will get stuck at m. If it is between m to m, it will show the actual value. If it is more than m, it will get stuck at capital M. This is the CDF of x. Your job is to sketch the CDF of y.